discuss about ray optics and optical instrument, class 12 physics. Okay, so we will continue. So this is the subtopic of ray optics and optical instrument, and the topic is refraction at spherical surfaces and by lenses. Okay. We have so far considered a refraction at a plane surface. We shall now consider refraction at a spherical interface between two transparent media. An infinitesimal part of the spherical surface can be regarded as planar, and the same laws of the refraction can be applied to every point on the surface. Just as for reflection by a spherical mirror, the normal at the point of incidence is perpendicular to the tangent plane for plane to a spherical surface that the point and therefore passes through the center of the curvature. We first consider the refraction by single spherical surface and followed it by thin lenses. A thin lens is a transparent optical medium bounded by two surfaces, at least one of which should be spherical. Applying the formula for image formation by a single spherical surface excessively at the two surfaces of a lens, we shall obtain the lens maker's formula and then the lens formula. Okay, so we will continue. Hello everyone. So next one is refraction at a spherical surface. Now figure 9.15. So this is the figure you can see as well. Okay, this is the figure and we will talk about this figure. So next one is the geometry of the formation of image of I of an object O on the principal axis of a spherical surface with the center of curvature C and radius of curvature, okay, R. The rays are incident from a medium of refractive index 1, index n1, okay, index n1 to another to refract index n2. As before, we take the aperture we take the aperture or the lateral size of the surface to be small compared to other distances, okay, involved, so the small angle approximation can be made. In particular, nm will be taken to be nearly equal to the length of the perpendicular from the point n on the principal axis. We have for small angles with tan angle NOM equal to nm upon OM, and we are talking about in this figure nm upon OM, nm, nm upon OM. Okay, so next one is tan nmc is equal to mn upon mc, that and tan nim is equal to mn upon mi. Now for triangle NOC in this figure, NOC in this figure, I is the exterior angle, I is the exterior angle equal to, so therefore angle NOM plus NCM equal to, that means I equal to mn upon OM plus mn upon MC. Similarly, we can also write R equal to angle NCM, N sorry NCM, NCM, okay, minus NIM, NIM. Okay, so next one is We can write also by Snell's law n1 sin I is equal to n2 sin r for small angles n1 I is equal to n2 r. Substituting I and r from equation 9, 10, 13 and 14. So n1 upon om plus n2 upon mi equal to n2 minus n1 upon cm. Okay. So om, mi, mc represent the magnitude of the distances applying Cartesian sign convention. Okay. So om is equal to minus u, mi is equal to plus v, and mc is equal to plus r in this figure. We are talking about in this figure. Okay. So next one, we will substitute in figure 9.5, sorry, in equation 9.15 in this equation. N2 upon v minus n1 upon u equal to n2 minus n1 upon r. Now, let us relation sorry, this equation gives a relation between two objects and a image distance in terms of the refractive index of the medium and the radius of curvature of the curved spherical surface. In it hold of any curved surface, sorry, spherical surface. Sorry. So next one is, the next subtopic is reflection by lens, and this is the figure. Okay, this is the figure, and we are talking about in this figure. Now, figure 9.16. These are the figure we will talk. So it shows that the geometry of the image formation by a double convex lens. The image formation can be seen in terms of the two steps. The first one is the first reflecting surface from the image I1 of the object O. The image I1 acts as a virtual object of the second surface that forms the image I at 9.16 in this figure. Okay, applying the n1 upon ob plus n2 upon b1 plus sorry equal to n2 minus n1 upon bc1. A similar procedure applied to the second interface ADC, A, ADC, ADC. Okay, it is a state. So it will give minus n2 upon di1 plus n1 upon di equal to n2 minus n1 upon dc2. Okay, for a thin lens bi1, b, where is b? B and I, b, I1. So next one is d equal to di1, adding equal 9.17 and 9.18. Okay. n1 upon ob plus n1 upon di equal to, we can take common n2 minus n1 and 1 upon bc1 plus 1 upon dc2. This is also equation. Suppose the object is at infinity. Okay, ob is tends to infinity and di is equal to f. n1 upon f equal to n2 minus n1 in common, and we can write 1 upon bc1 plus 1 upon dc2. Okay. So next one is the point where the image of an object placed at the infinity is formed is called the focus f of the focus f of the lens, and the distance f gives the its focal length. A lens has two foci f and f dash on either side of it by the sign convention. bc1 equal to plus r1, dc2 equal to minus r2. Okay. So 1 upon f n21 minus 1 in common, and 1 upon r1 minus 1 upon r2, where n21 equal to n1 upon n2. Okay. Now this is the equation, and it's take as the lens maker's formula. Lens maker's formula. It is useful to design lenses of the desired focal length using surfaces of suitable radii of the curvature. Note that the formula is true for the concave lens is so also that the case R1 is negative, R2 positive, and therefore F is negative. Okay, so we can see in the next page. Okay, now n1 upon ob plus n1 upon di equal to n1 upon f. So that's why in the thin lens approximation, B and D are the both close to optical center of the lens. Applying design convention, DO is equal to minus U and DI is equal to plus V. 1 upon V minus 1 upon E is equal to 1 upon F. Okay, equation 9.23. This is the 23. Is a familiar thin less formula, though we derived it for a real image found by a convex lens. The formula is valid for both convex as well as concave lenses and both the real and virtual images. Okay, it is worth mentioning that the two foci f and f dash on the double convex or concave lens are equidistant from the optical center. The focus on the side of the original source of the light is called the first focal point, whereas the other is called the second focal point. Okay. To find the image of an object by lens, we can, in principle, we take two rays emanating from point on a object, trace their path using laws of the refraction, and find out the point where the refracted rays meet be appear to meet. In practice, however, it is convenient to choose any of the following rays. Array emanating from the object parallel to the principal, and we are talking about in this figure. Okay, we are talking about in this figure in both one by one. Array emanating from the object parallel to the principal axis of the lens after refraction passes through the second principal focus f. Convex lens, in a convex lens, appear to the diverge in a concave lens from the first principal focus f. Okay, the second one is array of light passing through the optical center of the lens emerges without any deviation after refraction. Okay, third one is array of light passing through the first principal focus of the convex lens emerges parallel to the principal axis after refraction. Okay, array of light incident on a concave lens appearing to meet the principal axis at the second focus point emerges parallel to the principal axis after refraction. Okay, in B. Okay, in this figure. Okay, so next one is 9.17 and 9 AB in both figure. Okay, for a convex and concave lens, respectively, you should practice drawing similar ray diagram. Okay, this is the BBI, very important. In the different position of the object with the respect to the lens, and also verify that the lens formula, okay, and holds good for all cases. Here again, it must be remembered that each point an object gives out infinite number of the rays. All these rays will pass through a same image point of the after a refraction at the lens. Magnification produced by a lens is defined like that of the mirror as the ratio of the size of image to that of the object proceeding. Okay. In the same way, for a spherical mirror, it is easily seen that for a lens, magnification is equal to h dash upon h, that means v by u, where we apply the sign convention. We see the for erect or virtual image found by a convex or concave lens, m is positive, while for an inverted image m is negative. Okay, so next one is, now we will continue the power of lens. Next subtopic is power of lens. Power of lens, and we will talk in this figure. Okay, See, the power of lens is a measure of the convergence or divergence. Okay, which is a lens of introduction in light falling on it. Clearly, a lens of shorter focal length bends the incident light more while converging it in case of the convex lens and diverging it in case of concave lens. The power P of a lens is defined as the tangent of the angle by which it converge, okay, or diverge. A beam of light parallel to the principal axis falling at unit distance from the optical center, and we can say, sorry, we can take tan sigma. Hold on. Delta. Tan delta h upon f. If h is equal to 1, then tan delta 1 upon f, or delta is equal to 1 upon f for a small values of the delta. F is equal to 1 plum plum. P is equal to 1 upon f, where power is, we can define power is equal to 1 upon focus. The SI unit of the power of a lens is diopter. 1D is equal to 1 per meter. Okay. The power of a lens of the focal length of the 1 meter is 1 diopter. Okay. The next one, power of a lens is positive for a converging lens or and a negative for diverging. Okay. This is important point. Converging lens is positive power and in diverging lens negative power. Thus, we can say when an optician prescribes corrective lens of the power plus 2.5D, this required lens is convex lens of focal length plus 40 centimeter and lens of the power of the minus 4 D diopter means concave lens of the focal length minus 25 centimeter. Okay, thank you for watching.